Hello, this video presents the third part of Hypothesis Tests 2 in the QED module in Dev. And we're trying to work out here whether in the whole population of students, the proportion of Pro-Aid students is not higher in Dev or whether it is higher in Dev. And the problem is that we can only observe a sample, and in the sample it could be that among the Dev students it's lower or the same or just a bit higher, or it could be a lot higher among the Dev students. And unfortunately, when we observed, whichever one we observe, that could have come, as I showed you here, whichever one you observe could have come from either population. So this is where we can try and use a hypothesis test to tell us a bit more about which possibility is true. Now, the next diagram is an important one because I've tried to capture here the basis of all statistics tests, the logic that underlies all statistic tests. And the details vary between different tests, but the overall logic is the same. And this is where you have a theory about the world that you want to test, an idea or a hypothesis about the world. And with that theory about the world, you then gather some observations and you look at the observations. And the question you ask yourself is, if my theory is correct, what is the probability that I can see an observation like this one? And you see how unlikely it is. And if it's fairly likely, then that means your theory is probably quite good. If it's incredibly unlikely, it means that either something very surprising has happened or maybe this theory is not so great. Examples, maybe you have a theory that, I'll take a crazy example first, you have a theory that birds can't actually fly, and the reason that you sometimes see birds in the air is because just gusts of wind have blown them up in the air, or maybe someone has thrown them. So that's your theory. The observation is that pretty much every day you see birds that seem to be going through the air. So could it be that there's maybe a gust of wind every time you see them, or someone's thrown them, or they've dropped from an aeroplane or something? Could be, but if your theory is true that birds can't on the whole fly at all, the chance of seeing so many birds in the air just because of random gusts of wind, the tester here, the universal test, will probably tell you that's really, really, really unlikely, that it just happens that they're blown into the air by the wind. So maybe that theory that birds can't fly is not one you want to stake your reputation on. So maybe that's wrong. To take a more sort of sensible example, we can go back to the example of fast crops that we had from a previous workshop. You might observe that some farmers have moved from tree crops to fast crops. And let's say your theory about the world is that really that is the way to ruin. That's not going to help their income at all. And then your theory then is that that's a bad thing economically, but your observation perhaps is that you observe that all these people that have switched to fast crops, suddenly they're educating their children, they're well dressed, they're buying motorbikes, they're doing up their houses, they seem to have a high income. And okay, well, what could that be? It could be that it's just the ones you happen to observe because of the places you happen to pass by, or because the way you picked those people, for some reason there was just luck, meant that the ones you happen to observe who have switched to fast crops, just by fluke, those are the ones who also are doing pretty well. So then you want to use your universal test to say, okay, let's assume I did take a proper random sample. What's the chance that just by luck I can get a random sample of people where the fast crop people have done really, really well, if in actual fact my theory that fast crops do not help your income is correct? Then if the chance that you can randomly select people and see people who've switched to fast crops who've done really well, if it's quite a high chance, then okay, maybe that means your theories can be consistent, you can live with it. If it's incredibly unlikely, then you might want to reject that theory. So that's how all tests work. Okay, let's carry on, and that's the rule. If an assumed theory makes the observation too unlikely, we reject it. Small language then. So hypothesis, this is a more precise way of saying a theory about the way the world is, or a possibility. Sometimes called a theory about the world in the last lecture. For example, a hypothesis here would be that the percentage of Pro-Aid students is not higher in Dev than it is in non-Dev. That's a hypothesis. Normally you state things more precisely like this. So the proportion of people who would give Pro-Aid responses is not higher among Dev students than among non-Dev students. So being specific about what you're talking about is what proportion of people would give this response, and you're talking about the whole population of Dev students and non-Dev students. Now, simple tests of this type we'll do in the next couple of lectures help you decide between just two hypotheses. So one of the hypotheses has got got to let you work out these exact probabilities. And normally that's the one that we take and we call the null hypothesis. The other one's called the alternative hypothesis. And one thing about the null hypothesis is that it must let you work out the exact probabilities of observations. The other thing is that the null and the alternative must be exhaustive and mutually exclusive. Exhaustive means that there aren't any other possibilities. So it's got to be either this or this. Mutually exclusive means that if this one's true, this one must be false. If this one's true, this one must be false. They don't overlap. A common shorthand you'll see throughout the notes and the textbooks and so on is this, that H0 means the null hypothesis, H1 is alternative hypothesis. Sometimes this is written as HA. I'm going to write it as H0 and H1 for null and alternative. So now we come to the language of reject. And the idea here is that if you observe something which has got a very low chance of happening, if the hypothesis is true, then you reject the hypothesis. And logically that means that you must then accept the other hypothesis because they are exclusive and exhaustive. Now, strong support for a hypothesis can't be shown unless you reject the other hypothesis. And I'll justify this in a minute. This means that normally the one you hope to support is phrased as the alternative, and the one you hope to reject is the null. And a famous example of that is the black swan example. So suppose you had an idea that all swans in the world are white, and you want to find some evidence to support that. Well, you might go out and find, you see, oh, there's a white swan, that supports it. You might go to another river or lake and you see 5 white swans, and that supports it even more strongly. Then you spend a long while doing this and you find hundreds of white swans, thousands of white swans. That supports your hypothesis pretty well. It's pretty good confirmation, but it's not really quite so strong as the day you go out and you see a black swan, because that completely wipes out your hypothesis. So it's the hypothesis that you have supported very strongly is all swans are not white. So you can find very strong support for the hypothesis all swans are not white by setting that up as the alternative and then showing that the hypothesis all swans are right is false. So once you've shown the other one is false, then the alternative then becomes really strongly supported. So that's another reason for setting up the hypothesis in this way. Now, unfortunately, hypothesis testing is all about probability and likelihood, and things can go wrong. You're dealing in probabilities and not certainties, so there is always the possibility you're going to get an error. Because of that, you need to be as clear as you can about what goes on with errors. And logically, there are 2 kinds of error. One is that the null hypothesis is true, but unfortunately you reject it. And because if the null hypothesis is true, then you should not reject it, but sometimes the test result makes you reject it. That's called a type 1 error. On the other hand, it could be false, in which case you should reject it, but sometimes the test goes wrong and you don't reject it. That's called a type 2 error. And these are conceptually quite different. One way of trying to show these things is to go back to our friend, the tree diagram, as in probability. Here we think of nature as making the first move. Either H0 is true or it's false, but we can't observe that directly. All we can do is observe the test result and see, is it saying reject or not reject? And the idea is that here is where we get a reject result, and there we don't get a not reject result. And we'll see the kind of thing that reject and not reject looks like later. The problem is that when you get reject, you don't know whether you're here or here. When you get do not reject, you don't know if you're here or here. So if you say reject and H0 is false, that's great, you're here, you've made the right decision. If you say reject and unfortunately you're here, H0 is actually true and you've said reject, but you're wrong, so that's a type 1 error. Similarly, if you say do not reject, when H0 is true, that's what should happen. But if H0 is false, you should reject it. So if H0 is false and you say do not reject, you've made another error, but this is a type 2 error. So think about this and try and make sure you're clear that they're both wrong, they're wrong in different ways, the type 1 way and the type 2 way. So on the tree diagram, the probabilities are shown on the branches. So that's the probability of going up here, that's the probability H is true, probability H is false, in other words H1 is true. That's the probability of getting a reject result, alpha, so this must be 1 alpha. That's the probability of getting a do not reject result if H0 is false, beta, and that's 1 minus beta if you're getting a reject if it's false. This is beta is the probability of a do not reject if h naught is false, and 1 minus beta is the probability of reject if h naught is false. Now, all tests are going to tell you the alpha. That's basically what you get from the results of your test most of the time. Alpha is the probability of rejection if h naught is true. In other words, the probability of making a type 1 error if h naught is true. Unfortunately, we very rarely know what b is, which is the probability of making a type 2 error if h naught is false. And in the technical jargon, we say that if we get a reject result with the probability alpha of less than 0.05, we say we reject h naught with 95% confidence. If alpha is less than 0.01, 1%, we say we reject h naught with 99% confidence. And we'll get loads and loads of examples of this in the lectures and workshops and the lab. So, going back to the tree diagram, I've modified it slightly. What we try and do is we set it up so that if h naught is true, this is much more likely than this. So we set this, we say the range of alphas we're going to reject is quite small. So only if alpha gets to a really small level are we going to reject it, because then we know that if we get a reject result, it's quite unlikely that we came down here, whereas we set this one up so this is much more likely. So if we see reject, it's much more likely we came down this tube than we came down this tube. So because that's much more likely, we say if we see reject, it's likely to have been h naught is false, but there's still going to be this chance that we made a type 1 error. Similarly, we make this really narrow up here, so if we see do not reject, probably we're here. But even so, it's possible we'll say do not reject and we did come along this line, which means it's a type 2 error. So these are the meanings of alpha, the test probability, and beta, and the meaning of reject, don't reject, and type 1 and type 2 errors. And then we'll go back and apply this in a minute to the ongoing example of the dev student supporting aid or not supporting aid. Thanks for watching.